Hello everyone, and welcome to the video on right triangle trigonometry. In this case, our skill objectives for this video are number one, to learn the trig functions or ratios of sides of right triangles. Number two, evaluate trigonometric functions exactly for special angles. And the third one, evaluate trigonometric functions using a calculator. Our conceptual objectives on this is one, understand that right triangle ratios are based on similar triangles, and number two, understand the difference between evaluating trigonometric functions exactly and using a calculator. Let's start out by looking at similar triangles. The reason we want to do this is because we're going to be working with specific angles, and we're going to go and have six trig functions, and we're going to want to be able to plug an angle in and get the value out. The value that we get for like the sine or cosine or tangent of one of these angles does not depend on the length of the sides because of the fact that we're working with the similar triangles, so there's a ratio that they work with, so that when the angles are always going to be the same, the side lengths might be different, but the ratios will be constant. So when we talk about similar triangles, these are triangles with corresponding angle measures. Now what that means is all the angles of the triangles are equal, in that we have this angle here, and that angle will be the same measure. This angle between the hypotenuse and the leg labeled B is going to be equal to this one right there. And we have two right angles, so that we know those are equal, but these two angles would also have to be equal. And if the triangles are similar, then I know that the ratio of A over A prime, this one, is going to be equal to the ratio of B over B prime, and that will be the same as the ratio from C over C prime. Now when you work with similar triangles, I always try to go and have a pattern, and I use this pattern here. I'll put we have a larger triangle and a smaller triangle, so I have the side lengths of the larger triangle over the side lengths of the smaller triangle. So what this really allows me to do is say that if I'm talking about, let's say, a sine of a 30-degree angle, that whether I'm talking about this angle here or this one, the sine of 30 degrees would come out to be the same value for each triangle. Now let's look at a right triangle. When we talk about a right triangle, obviously it's going to have a right angle, and there'll be some notation for us to recognize the right angle. And then we'll have the two other angles. Now I've labeled these two angles. This one is theta, and that is the Greek letter alpha. And when I look at a right triangle, I know that the side opposite of the right angle is called the hypotenuse, and then the other two sides are called the legs. Now when we talk about these angles, theta and alpha, one of the things that's going to be important for you to do is we're going to be talking about the leg that's opposite the angle and the leg that's adjacent to the angle. When we talk about an opposite leg, for example, like with theta, the opposite leg is going to be the leg that is on the exact opposite side of the triangle from theta. The adjacent leg is going to be the leg that makes up part of angle theta, like this leg there. So when I'm working with this one, I know for theta, the opposite leg is equal to A, and the adjacent leg is equal to B. Now for alpha, it's going to be a little bit different. Because of now alpha is up here, the leg opposite, on the opposite side of the triangle, is going to be over here. The leg that makes up part of alpha is this one. So for alpha, the opposite leg is equal to B, and the adjacent leg is equal to A. Now when we're working with this, we're going to use this in a few minutes to help us identify values of the trig functions. And you've got to be aware of, when you're talking about an angle, what leg is going to be opposite, what leg is going to be adjacent. Now, we do have 6 trig functions, and you're all familiar with the sine, cosine, and tangent. Sine of theta, cosine theta, tangent theta. Those are the 3 that appear on your calculator. There are two or three other ones. One of them is called the cosecant. And the cosecant of theta is CSC of theta. And that is equal to 1 over the sine of theta. It's the reciprocal of sine. Cosine has a reciprocal, and that reciprocal is the secant. And tangent of theta has a reciprocal, and that reciprocal is called the cotangent. Now, the other thing that causes problems is if you look at your calculator, you will notice that the second function for sine, cosine, tangent, if you look right above the sine, cosine, and tangent buttons, you will see, for sine, you will see sine to the -1. It's important to remember that sine to the -1 here is not equal to 1 over the sine of theta. It is not equal to the cosecant of theta. Okay? And the same thing is true for cosine and tangent. So please, 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 when you are trying to find secant, cosecant, or cotangent, be sure to use these ideas right here, that they're the reciprocals of the sine, cosine, or tangent functions. Now the next thing we're going to do when we deal with right triangle trigonometry is we do have this thing called SOH-CAH-TOA. Many of you will remember it from geometry. Some may remember it from last year as well. When you dealt with what it means is sine, SOH-CAH-TOA, tells us it's an acronym to help us identify the relationships that will give us sine, cosine, and tangent. The SOH means that the sine of theta is going to be the length of the opposite leg over the length of the hypotenuse. The CAH, cosine of theta, is the length of the adjacent leg over the hypotenuse. And the tangent, TOA, tangent, is the length of the opposite leg over the adjacent leg. Now, because of the reciprocal nature, too, once I know what the sine is, I do know that the cosecant of theta is going to be the hypotenuse over the length of that opposite leg. I know that the secant of theta is going to be the hypotenuse over the adjacent leg. And I know the cotangent of theta is going to be the length of the adjacent leg over the length of the opposite leg. You do want to make sure that you are very comfortable with these and have these memorized. Now, really, if you just remember that acronym, it can help with all of them. And these will be important for us as we're moving forward with some of the problems we do today and later on as well. Let's take a look at a problem that we have. In this case, we want to find the value of all 6 trig functions using the given triangle. And in this case, I have this triangle here. I know that my angle is theta right there, and that this leg is 3, the length of this side is 4, and that is 5. You can check that with the Pythagorean theorem. Those are 3 numbers that do satisfy the Pythagorean theorem. And so when I look at this, I want to find the sine of theta. Well, I know by SOH-CAH-TOA, sine is opposite over hypotenuse. So the length of the opposite side on this one, the length of the opposite side is 4. The length of the hypotenuse is 5, so the sine of theta in this case is 4/5. Because the cosecant is the reciprocal of that, I know the cosecant is going to be 5 over 4. Cosine of theta. Cosine is adjacent over hypotenuse. Well, in this case, the length of the adjacent leg is 3. The length of the hypotenuse is 5. And so the cosine of theta is going to be 3 over 5. The secant is the reciprocal of cosine, so I know the secant is going to be 5/3. The last one is the tangent, TOA. Tangent is opposite over adjacent. So our opposite leg is here, our adjacent leg is here. Because remember, theta is this angle. So the tangent in this case is going to be 4 over 3. And the cotangent, which is the reciprocal of tangent, is going to be 3 over 4. We're now going to make another little trip back to geometry, so a couple of years ago. When you were working in geometry, one of the things you dealt with triangles was that you had two special right triangles. One was the 30-60-90 triangle, and the other was the 45-45-90 triangle. And what was special about those is that you were able to go through and find all the lengths of all three sides of the triangle if you knew just one side, because there were relationships that existed. For example, in the 30-60-90 triangle, I know that I have a 30-degree angle. The side across the 30-degree angle is x. I know the side across from the 60-degree angle is x squared of 3, and the hypotenuse was 2x. And so what that did is it allowed me to go and say, hey, if I know that the shorter leg was equal to 5, so if I know that's 5, then I would know that the hypotenuse is going to be 2 times 5, which would be 10, and the longer leg would have been 5 times the square root of 3. So I would have just had 5 square root of 3. Well, that relationship, and remember, since these are all similar, it doesn't matter how big or how small the triangle is, the angle, as long as the angle measures are the same, we're okay. That allows us to go through and use these to come up with exact values for the sine, cosine, and tangent of an angle. What I can do is this. I know that if I look at 30-degree angle, the 30-degree angle here, I know the sine of 30 degrees is going to be the opposite over the hypotenuse. So in that case, when I do the length of the opposite side, I get x over 2x. But if I reduce that, I can reduce out the x and I'll be left with 1/2. So I know that the sine of a 30-degree angle is going to be 1/2. The cosine of a 30-degree angle. Cosine is adjacent over hypotenuse. And so the cosine of that 30-degree angle is going to be x times the square root of 3 over 2x. And when I reduce that, I get square root 3 over 2. The last one is tangent. Tangent is opposite over adjacent. So here's our opposite. There's our adjacent to 30 degrees. And so I know the tangent in this case is going to be x over x square root of 3. Well, this one, if I reduce it, I get 1 over the square root of 3. And if I'm going to rationalize that denominator, I need to multiply top and bottom by square root 3. And I get that the tangent of 30 degrees is square root 3 over 3. Those are the exact values for the sine, cosine, and tangent of 30 degrees. What I'd like you to do right now is I would like you to pause the video, and I would like you to go and calculate, use this triangle, to find the exact values for the sine, cosine, and tangent of 60 degrees. Welcome back. In this case, you should have gone through and calculated. You come up with your calculations for the sine, cosine, and tangent of 60 degrees. What you should have got for the sine of 60 degrees is square root 3 over 2. The tangent of 60 degrees should be 1/2. Or sorry, the cosine of 60 degrees should be 1/2. The tangent of 60 degrees should have come out to be square root of 3 over 1, or just square root 3. Now, once you have those, you could also go and find the secant, cosecant, cotangent of 30 and 60 degrees just by taking these reciprocals and, of course, rationalizing those denominators as well. Now let's take a look at the 45-45-90 special right triangle. So in this case, I have that this is isosceles right triangle. Those are both 45 degrees. And what you have is that since they have it's isosceles, I know that the legs have the same length. So they're both x. And the hypotenuse is x times the square root of 2. So what you need to do now, I want you to pause the video and use this same thing that we just did. I would like you to go and find the sine, cosine, and tangent of 45 degrees. Get it reduced and also rationalize the denominators. Okay, welcome back. In this case, when you went through and did the sine of 45 degrees, sine, and it doesn't matter, when I look here, I can take this one or this one. I'm going to use this one right there, the one here at the base. And I'm going to go through, the sine is opposite over hypotenuse. So in this case, when I did the sine of 45 degrees, that would have been x over x square root of 2. When I reduce it, I get 1 over the square root of 2. And so when you rationalize that denominator, you'd have to go through, and multiply top and bottom by square root 2. So you'd end up with square root 2 over 2. Cosine of 45 degrees, well, if you notice, you're going to end up getting the same thing. You'll get x over x square root of 2. So you'll get 1 over the square root of 2. And again, multiply top and bottom by square root 2. And I get square root 2 over 2. The tangent of 45 degrees, when you do that, you get x, it's opposite over adjacent, so I get x over x. So the tangent of 45 degrees comes out to be 1. I hope this matched with what you came up with, and now let's move on. What I have here, this is a table for the trig values for special angles. So what you see over here is degrees and radian measures. So 30 degrees, if you can use the conversion, that is pi over 6 radians. 45 degrees is pi over 4 radians, and 60 degrees is pi over 3 radians. And what you see, those are possible measures for theta, and then you'll see across here sine of theta, cosine theta, tangent theta, cotangent theta, secant theta, and cosecant theta. So what happens is the pairings are you start at the outside and then work your way in. Those are the ones that are paired together. Sine is and cosecant are reciprocals. Cosine and secant are reciprocals. Tangent and cotangent are reciprocals. And so what you see here is if I want to know, this goes through and says that the sine of 30 degrees is 1/2. Cosine is square root 3 over 2. Tangent is square root 3 over 3, which we already did. Cotangent will be the square root of 3. Secant is going to be 2 square roots of 3 over 3. And cosecant is 2. You want to go and pause this video and get this written down. Some of you will remember this from the unit circle last year. This is the same numbers you dealt with, only when you worked with the unit circle, you would have just had these values right here. And I want you to go through and make sure you copy these down because you're going to want to go and get these ones memorized as we proceed, because these are going to be values that are going to come up many, many times. So pause the video, get this written down, and then we'll progress forward. Okay, now let's move on to an application problem. Now the key on any application problem is that you have to identify the right triangle. So what I have here is I have a man is 100 feet from the base of a building. The triangle, the angle of elevation from the man to the top of the building is 75 degrees. And we want to know how tall is that building. Okay, so one of the things you're going to want to do is make a diagram. I know everybody always says, why do I have to make that, blah, blah, blah. But making a diagram is going to be helpful for you to identify that triangle. So here I went and drew the building. I drew my man, and I said that's 100 feet. And I know that the angle of elevation from the man to the top of the building is 75 degrees, so I drew that in. And once I did that, you get this triangle, and that happens to be a right triangle. We're trying to find the height of the building. We know this angle is 75 degrees. And so now what I can do, once I've identified that triangle, I need to go through and take the pieces of information I've given, the 75 degrees and the 100, and tie it to the piece that I'm trying to find, which is the height of the building, which I've labeled as x. So I have to look at that, and I have to identify, see the right triangle, and I ask myself, what trig relationship, which one of the SOH-CAH-TOA relationships ties these three pieces of information together? And what I know when I look at that is I know that the tangent ties these together. I know that by SOH-CAH-TOA, I know the tangent of 75 degrees is going to be opposite, which is x, over 100. So now I need to solve it for x. Well, to do that, I'll multiply both sides by 100. So I'm going to get 100 times the tangent of 75 degrees equals x. At this point, I can just go plug it into my calculator and see what I get. So I take that when I go through. Well, I'll tell you what. Why don't you pause the video, put that into your calculator, and then when you get done, let's see what you came up with. Welcome back. You should have come up with that the height of the building is about 373 feet. Okay, now if you didn't, if you got something different, one of the issues we have in this chapter when we're working on these things is the idea of the mode. A lot of you have asked me at various times throughout the year if we need to be in degree mode or radian mode. What you have to remember when working with these. Anytime you work with a trig function, you have to be aware of the mode. If you're working in degrees, if you're given an angle in degrees, your angle measure is in degrees, you want your calculator to be in degree mode. If your angle measure is in radians, you want your calculator to be in radian mode. So one of the things to do that, you press your mode button, and you can see degrees or radians, highlight the one that you need to use. So in this case, because I'm given the angle in degrees, I should be in degree mode. So if you didn't get the 373.2 feet, check your answer and see, check your calculator, see if you are in the proper mode. This now concludes the video on right triangle trigonometry. We will take a look at a couple other things in class, one of those being bearing, another way of doing a story problem is with bearing. And also going through and solving an application problem, how to solve an application problem where what we're looking for is an angle measure. So we'll do that in class along with the bearing, and other than that, though, you should be in pretty good shape for completing the assignment. So we will see you in our next class.